Let's go to our question 7. We'll do for the following: for absolute value of z minus 4 divided by z equals, say, 1, show the geometric interpretation. So, if you remember from the previous example, when you have something like z absolute value minus something, that's the distance between z and that other z1 value, so call it z1. So distance. And what would you do first? So instead of doing that, so first thing would be what comes in mind, that one of the useful formulas is the absolute value, the modulus of z divided by z1 equals modulus of z divided by modulus of z1. So if you apply that rule, the previous becomes z minus 4 modulus divided by z modulus equals 1. From there we get z minus 4 equals z modulus. So this z we can write as z minus 0, z minus 4. So this becomes, if you look at our previous example, that tells us what is the locus of points equally distant from minus 4 and 0. So from 4 and 0. So graphically, that would be 1, 2, 3, 4. So that z number here is x coordinate is 4 and imaginary is 0. So a real part of this z number, z1, so the second component of z, is x equals 4. So a real part is 4. This is imaginary of z. And the other one equally distant from z equals 0, so that's the one here. So what's equally distant? It's locus of points on this vertical here. So graphically, solving this would give us that a real part of z equals 2. The other way to solving this, that's one way. The other way would be you break down z into x plus iy minus 4 equals to x plus iy. So apply the modulus, you get x minus 4, that's the real part, and this is the imaginary part. So you get the real part plus the imaginary part. So the modulus would say that's x minus 4 square plus y square equals x square plus y square. Lose the roots, you get x minus 4 square plus y square equals x square plus y square. Lose squared y on the second power 2, so you get x squared minus 8x plus 16 equals x squared. You lose x squared. From here you're getting that 8x is 16, therefore x is 2. So the real number, so that's equal, the real part of z equals 2. So that's two ways to solve question 7. Two ways. One way is that, including the picture. The other way is when you break down that. So that's our question 7 finished. First we will do is analyze what we got here. So let's take a green color, and if you extend this line here, we can see that the line is crossing there. So what is the equation here? Points z1 and z2 are both here. So if we say every point got a vector, so you have a vector is here, that's vector 1 for z1, and this is a vector for z2. Therefore, what would be the vector z minus z1? That vector would be z is the like vector here. So say this vector z. So z minus z1 will be from z1 vector pointing here. That would be that vector. Let's do it in red. That's z minus z1 vector. Z minus z1. So that's our first vector. So what would be then the vector? Let's change the color to say green. What would be z minus z2? Z minus z2, according to our diagrams at the beginning, is from z2 pointing to z, so that will be this vector here. So what do we see? That these vectors are collinear. So these points are then collinear. And that happens when we can say, in this case, we can say, let's change the color, that argument of z minus z1 is equal to argument of z minus z2, but in the opposite direction. So if you put it here, if this argument, so the red one, the argument is, see, it's pointing down, therefore the argument is here. That's the argument of z minus z1. And where is the argument of z minus z2? It's from here all the way up to here. That's the other argument. So that's our argument here. That's argument z minus z1 is here. And argument z minus z2 is here. So what we can see here, if I do another line here, so they both add up to 180. So what that means in this case, that argument of z minus z2, this is this one, plus this one, z minus z1 will be 1 pi. So z minus z1 would be this one, would be a pi minus z minus z2. So z minus z2 so you can say z minus z2 plus this one equals pi so it's pi minus this. So we have this bit plus pi. So we have this bit plus pi. If we write it that a bit neater, plus pi equals argument of z minus z2. Let's go with our next question, question 9. From the above, what does z equals z2 minus z1 represent? What is z2 minus z1? So let's have a look at that. So again we're going to a red column. So what that would be? That would be a vector pointing from the end of z1 towards z2. So the vector would be from here to here. So, and if you do it, so it would be like this vector. So if you put it from the origin, that vector would be that. That would be our vector z2 minus z1. So, but that doesn't represent a locus of points, it's just a vector. The answer to 9 is, it is just a vector, not a locus of points. It's our answer number 9. So just let know this is our answer. Sorry for that. And This is our answer number 8. And this is our answer number 9. Let's continue with one last question. Question number 10. Question number 10. From the above, what does argument of z minus z1 equal argument of z minus z2 represent? There is no pi here. So there is pi here, but no pi here. So the answer number 10 would be, see, notice that argument z minus z1 is equal to, so equal sign means that both vectors point the arguments that are equal. Equal sign for arguments means, that both arguments, which is angled, both arguments, argument z minus 1 equals argument z, point in the same direction, because see here the arguments are the angle, so the angles are in the same direction. So that means that, this arrow and the green arrow point in the same direction, So if you draw this picture again, maybe it will be easier to see. So let's do it again. So you have one point here, one point there, z1, z2, and then you have them pointing both in the same direction. So you have z, if you put z here, then you can see what happens. They are on the same line, they're collinear. That means that the arguments are the same, but the direction. So let's see, the first was red. So the direction was z minus z1, so z1 to pointing to z, argument is z minus z1, so that's 1, that's 2, z minus z1, and that's that way. So now, if you change the colors, and what's z minus z2? Z minus z2 is from z2 to z1, to z, sorry, that's that vector. So you have both vectors, are in the same direction. So what that means is that z, in this case, is a locus of points on this line. It's a ray there. obviously the argument is there. From Z onwards. So this case happens when I've gotten that Z2. This case happens for every Z past point Z1. So this is the point Z1. So Z can be anywhere past point Z1 to the left. Let's start with question 11. And the question 11 is question 11 will be, how do we represent parabola in complex plane, in the complex plane? So let's draw a parabola. The best how to represent a parabola in the complex plane. So let's do a parabola. Say that our parabola is got a focus at 1, 1, and its vertex is here. So say it might look something like that, and something like that. So vertex is the point one, 1, and sorry, 1, 0, that's our vertex, and our focus is the point 1, 1. So we know the definition of the parabola. It says that it is a set of points equidistant from the focus and the directrix. So where is the directrix here? So let's first write the equation. The common equation of a parabola will be y minus h, sorry, x minus square h, in this case, minus h squared equals 4 times p times y minus k. So our vertex is the point called h k, and our focus, f for focus, vertex, focus is the point of h k plus that letter p. That's the distance, the distance p. So how do we call it? So what's our h here? So if you look at there, we have h equals 1. Then you have k equals vertex 0, hk, vertex H and K. And what's our P? From the focus, you have K plus P equals to, what's the focus? 1. From there, because K is 0, it follows P equals 1. So what we got H, K, and P. So that's the common equation of the parabola. So the equation becomes h minus x minus h square equals 4 times y minus k is just y, 4y. That's our equation. That's a bit better written. It's y equals x minus 1 square divided by 4. We can write it here, it's better. Y equals x minus 1 square divided by 4. That's the equation of the parabola in Cartesian plane. So what's our directress? We need it because the parabola is defined as a set of points equidistant from the focus, there, focus, and the directress. Our directress has the equation of y equals k minus p. So that becomes 0 minus 1 is y equal to minus 1. So that's our directress. So the division of the parabola is set of points equidistant from the directress and the focus. So if that's minus 1 here, so let's get our directress is here. That's y equals minus 1. So what is that set of points? This set of points here represent our z, locus of points. So if our z is here, let's change the color. That's our z, and it has coordinates of x and y, of course, because z is equal, as we said, z is equal x plus e I y. So that's your imaginary, which is y, and that's what your real part. So what we say that this distance here is equal to this distance here, the same distance, and for the same of them, the same thing. So the distance there should be equal to the distance there. So this one and this one are the same, and so for this one too. Distance here and distance here, that the same. So what's the coordinate? So here, so these are the distances, they're the same. So what's the distance here? Let's call this point here this point here, call it Z1. So Z1 has the coordinates of the real part is 1. The imaginary part is 0. Yeah. So now, the distance, say, so how we can write that in complex plane, that would be 1 plus I. So 0, 1 plus 0, so it's 0, 1 plus 0, I. So what we're going to say? We're going to say that the distance between Z and the fixed point, which is focus, and the focus has coordinates of, where is our focus? Okay, so should I put it here, focus? Yeah, 1, 1. So the distance from Z to focus is the distance from the same as the Z to the directress. So the distance from Z to the focus, and focus is 1 plus I, is the same as what? In this case, for this distance here, so it's the same as, if you look at here, so say this way here, this one. So distance there is the same as, what's the coordinate to this one? Whatever that coordinate is, y. So this distance here is y, and it's always y. Which for every dot here, this distance to the vertical is y. For this dot here, it's our z. This distance here is again equal to y. That's the coordinate to z. So that's distance, say for this point, is distance of y from here to here plus the distance from the real the x-axis to the directress. Yeah. So, and where is the directress? Directress is at -1. So what we're getting is the same as, so the distance there is the same as whatever the coordinate is of z. So it's imaginary part of z, that's our y coordinate, plus distance from 0 to the directress is 1. So that will be our equation. Our equation of in the complex plane of that parabola. But there is, how do we prove it? Is that correct? Let's do it the other way. So it can be proven or can be written another way. And that is, we do know our equation of the parabola. Sorry, we do know our equation of the parabola in the Cartesian plane. That's our y. So that's definitely that equation. Let's prove that this is correct. The way to prove that this is correct, we need to come to be the same as the equation of the Cartesian plane, and that's when we put the coordinates for z. So let's prove it. So let's start here. Now z is x, so we're taking it from here. X plus ey minus the absolute value of that minus 1 minus I, imaginary of z, imaginary of z is y plus 1. So if we group like terms, that and that, and x and y, we get the absolute value x minus 1. And then we isolate I, and we get y here, and I minus 1. Absolute value of that equals y plus 1. So if you take the absolute value, what it is, a square, so that's x minus 1 square, sorry, not the absolute value, but apologized. So we take the distance here, the modulus. So the modulus there is plus y minus 1 square, and then square root of that, and then to remove it you apply square root on both. So you get, we can keep that, leave that step there, and the square root comes here, sorry, and here is y plus 1, then we put the 10 to the power of 2. So directress is here. We can remove the directress now. So what that becomes, it becomes x minus 1 square plus y minus 1, that's y square minus 2y plus 1 equals, and this is on square, because y square plus 2y plus 1, and what's the same on both sides, that's there, and what's left is x minus 1 square minus 2y on the other side goes and becomes 2y plus 2y is 4y. So we have proven, and from there we have that y equals to x minus 1 squared divided by 4. So we have proven that our Cartesian equation is equal to our complex equation. So we've proven the equality. Cartesian equation is an equation equals complex equation, and that's our proof that we've done it correctly. And just one more thing to circle our another one, or the complex equations, another form, broken down form, either that or this. Question 12. Find the equation from knowing the roots. find the equation when we know the roots. How do we do that? So better say how to find the equation when we know the roots. How to find, 12. How to find the equation when you know the roots. So say we know now the roots. The root is the only root is 1 plus I. No other real roots. What is the equation? So if you have one complex roots, we said that they always come in pairs. So the equation has to be. So what do we do? The roots are in the form of x minus alpha. That's the equation. The Cartesian equation is times x minus alpha complement, where alpha and alpha complement belongs to complex numbers. So that's because the roots have to be opposite, right? So you have x minus 1 plus I times x minus 1 minus I. So what does that become? Becomes x squared so you have x times plus x times minus 1 plus I x times minus 1 plus I. Then you have the second one plus x times 1 plus, so minus 1, sorry, minus 1 minus I and you have at the end plus 1 plus I times 1 minus I, and we know from before that comes to 2, just did it, and here we have x squared plus, sorry, minus x plus ix minus x minus ix plus 2, and the equation becomes plus ix and minus ix. The equation becomes x squared minus x plus 2. So that's our equation. for the complex roots. Let's prove this equation. What would be, so x squared minus x plus 2 equals 0. So x12 is minus b is 1 plus minus square root of b squared minus 4ac, that's 8, divided by 2, 1 plus minus square root of minus 7 divided by 2. I'm sorry, here is 2x, right? Minus 2x minus 2x. So that becomes, because this one and this one is 2x, so this becomes minus b is 4, minus b is 2, plus minus b squared is 4, minus ac is 8, so minus 4. Minus 4ac. So here is also 2, and here is minus 4. So what we're getting here, we're getting 1 plus minus square root of 4 can be written as minus, so square root of minus 1 is I, and times square root of 4 is 2 divided by 2. So this becomes 1 plus minus I. And we have proven that our equation is this. And that's our equation that we get from the square roots, knowing the square roots. So that's equals 0. Right? Here I say only root. So we should say no other real roots, and the only complex root, the only root in complex plane that we know, and it's only that one. So we say roots come in conjugate pairs. That's the most important. So whenever there's a root like that, there will be another root. Always. That's the point. You just put this under quotation marks, right? Because we know that conjugates exist.